Welcome. In this, the fourth of the videos in the gnuplot series, we are going to discuss how to fit known functions to the contents of data files. To illustrate this, I am going to go back to a data file which we had used back in video number 2. This file was called test.dat. And just to remind you, if I were to plot the data in that file, I would say plot followed by name of the data file within quotes, and this is what the data file would look like. Now I don't like the plus marker that is used for the data file points by default, so what I will do is I will change over to a marker which I do like, which is point type 7. Let me remind you that gnuplot allows abbreviations, so instead of having to type point type, you can just say pt7. And this is what the contents of the data file looks like. At least the first two columns look like when plotted with point type 7 filled circles. Remember, the first column of the data file is plotted along the x-axis or the horizontal axis. The second column is plotted along the vertical axis. Now, if you had such a data file from an experiment, you would obviously assume that the actual data should have borne a straight line relationship, and the only reason why you are seeing deviations from a perfect straight line must be because of experimental errors. So in such situations, we usually plot what is called the best fit straight line, a straight line which sort of best represents the data that is in front of us. So in this case, it is simple enough to do even by hand. You just take a look at the data, try to draw a straight line roughly down the middle of the data points with roughly equal number above and below and so on. But there is a very nice mathematical way of doing it. This is called the least square method. I'm not going to talk about the details of the least square method here, but we are going to show you how to use it in gnuplot, and for that we need to use the fit command. But before we use the fit command, let me define the function that I want to fit. In this case, it's going to be a simple straight line function, a into x plus b, because that of course is what the data looks like. Now that we have defined our function, what I need to do is to say fit followed by name of the function followed by name of the file, the data file, in this case test.dat, and then comes the most important part. I have to tell gnuplot which variables I am allowing it to vary in order to make the function that I have specified go as close to the data points as possible. In this case, I want to vary both a and b. I am allowing gnuplot to change both a and b from the starting values, which by default gnuplot takes to be 1. For that I have to say var followed by the variables which I am allowing gnuplot to vary, separated by commas. In this case there are only two variables, so a comma b. Now if I do this and hit enter, this works pretty quickly, and almost in no time we get this result. It says after 3 iterations the fit converged. These are numbers which you will need to pay attention to if you were interested in the details of this. But the really important thing for you is the value of a, which gnuplot is telling you is minus 1.97559 for the best fit, and the value of b, which it is telling you is 10.0134. It actually also gives you estimates of the error with these values, And what we see is this looks like a reasonably good fit because the errors are pretty small, around 1% and 0.5% for A and B respectively, as you can see here. But to see how good a fit this is, the best thing to do would be to plot the data points again along with the function that we have, and just to make the curve more visible, what I will do is I will plot it with line width 2, that is twice as wide as the usual line. And remember, once again I can use LW instead of line width. And let's see what happens. This is what you get. These were the data points, and right down the middle, this looks like a wonderfully good fit. This is the straight line which describes the graph. Now I'm not sure whether you remember, but our data file test.dat actually had 3 columns of data. And if I were to plot the first column versus the third column, I would have to use the using command for that. So it's plot followed by name of the file within quotes, then using 1:3 to tell gnuplot to plot the first column data along the x-axis and the data in the third column along the y-axis. And of course this is going to be different data, so I don't really want to plot f of x along with it. So let's just take a look at what the data looks like. This is what the data looked like, the third column versus the first column. And this looks rather like a neat parabola. Of course, again, you don't have an exact parabola. There are deviations, and presumably once again because of experimental error. So in this case, the curve that I would want to fit should be a parabolic curve, maybe m into x square plus n into x plus o. And in order to fit this, what I would do is I would say fit followed by name of the function followed by the name of the data file, including the using specifier to tell me what exactly do I want to fit. By the way, I could have used u instead of using here. That would have worked fine. And then I have to tell gnuplot which variables I am allowing it to vary. In this case, I am allowing it to vary all 3 of the variables or the parameters m, n, and o. Once again, by default, gnuplot starts with values of 1 for each of these variables and essentially tries to adjust these variables in such a way that you get the data to fit as close to the curve as possible. Once again, it has quickly given me a result, and it looks
from the sight of it like a pretty good result.
There are errors, but these errors are of the order of 1% and 3% here. To see how good this fit really is, let's plot the data, which is this command, along with the function, of course not f of x, but I fitted g of x here, and I will use line width 2 once again to see what this fit looks like now. And once again, you should be pretty pleased with the fit of this data. So as long as you are doing what is called a linear fit, the procedure is pretty straightforward. You just define the function and then say fit followed by name of the function followed by the name of the data file with using specifiers if you want them, and then say var and give a list of the variables you are going to allow gnuplot to vary. By the way, you can actually fit this part of the data. For example, if I think that there have been problems here with the data and the region between -3 to -1, let's say, actually represents my actual parameters much better, I might even be trying to fit a straight line to this part. Of course, I could even try to fit a straight line to the entire parabolic curve. Let me just show you what happens if I do that. So what I could do is go back to our original function f of x, which remember is a straight line a into x plus b, and try to fit that to the entire parabola all the way from -3 to +5 for x. And for that, of course, I have to say using 1:3, first column versus third column, and via the parameters a and b in f of x. I do that, I get a fit. Is this any good? Let's just see. I'll try plotting f of x with this. Look at a straight line, which with some amount of latitude you could say fits the parabolic curve somewhat. You get equal amounts of data above and below, which frankly is not a very good fit. And it's not expected to be. The whole curve definitely looks more like a parabola than a straight line. And if you try to fit a straight line forcibly to that, this is the best gnuplot could do. So gnuplot doesn't have a magic wand. If the data does not look like a straight line, it can't make it fit a straight line very well. However, as I was saying, it might be possible that I actually believe that the data was better between -3 and -1, and somehow this data here has been corrupted and we want to fit a straight line between this part of the data only. Well, I can do that. All I have to do is go back to the fit command and specify the x range to use. So I'm saying fit between -3 and -1, the function f of x, to just dot that. And now I have a fit which doesn't really look very nice. Let's just see. Is this any good? Well, actually it is. In the region where I believe the data is okay, I actually get a pretty good fit. In fact, to see this better, let's plot not over the entire range, but from -3, say to 0, and see what happens. Remember, I have only fitted from -3 to -1, so it's no wonder that these points are actually deviating quite a lot away. But in the region where I have fitted this, the straight line actually fits quite well. Now, I used the word linear fit a while ago, and I was not referring to the fact that ax plus b is a linear function of x, so that the graph is a straight line. Actually, if you remember, I was using the word linear fit in the context of the parabolic curve as well, where g of x was being used to fit the graph. The point is, when I use the word linear or non-linear here, what I mean is in the context of the parameters. The parameter, a and b in this case, and m, n and o for the parabola, the function were linear in those. And linear fit is always the easier thing to do. And with linear fit, gnuplot will always come up with a rather nice answer, provided, of course, the function you have chosen remotely looks like the data file that you have. To see an example of a nonlinear fit, let me now show you the result from a different data file. This data file is also in the directory that we are using. It's called res.dat. And if you look at the data in the file, once again let me plot it with point type 7. I'm pretty sure those of you with some knowledge of basic physics would immediately recognize why I am calling it res.dat. Well, you need a bit of imagination to do that, but you should be able to spy a resonance curve, a curve which has a peak here and then drops off, which is why this file is called res.dat. So what I want to do is fit the standard Lorentz curve for resonance to this particular data file. So let me remind you that in resonance in, say, a standard LCR circuit, the voltage, which presumably is the data that is being plotted against frequency, has a variation which looks like this. The voltage has a peak value V0, and as frequency is varied, the dependence of V on the frequency goes like this. So, to those of you who are familiar with this, you would realize that when f is equal to f0, you have the maximum value for V, so that is your resonance frequency. And you don't really have to be familiar with this to understand that. After all, the entire f dependence here is in the denominator. So, this is a function of f, as I have written down here. And you can see that the f dependence is in the form of a perfect square here. So denominator will be minimum, and hence the v of f will be maximum if this perfect square were to vanish. And that will happen when f is equal to f0. So this is the function that you are trying to fit into this particular graph. So let's give it a try. Let's first define the function. So let's define the function to be r of x, and rather than write v0 etc., I'm going to use the simple parameters a, b and c. So a for the v0 in that formula. Let's try to see both of them side by side. Let's make this a bit smaller so that you can see both together. Here a is standing in for v0, then you have to divide by the square root of the whole thing inside brackets. 1 plus, well, no point in writing q square, I can just write b into, now instead of f I have to use x, because to gnuplot the dependent variable is always x, at least for 2D graphs. So x by, well, I could say f0, but let's say c, doesn't matter, minus c by x, that has reproduced the bracket, then I have to square this. So my function r of x has been defined. So what I now need to do is to plot, or rather fit this function r of x to the data in this.dat. So let us try following the previous method. But before we do this, notice that my function is now linear in the parameter a, definitely, but it is not linear in the parameter b. That is inside the square root. It's perhaps even more non-linear in the parameter c. So this is a non-linear fit in terms of the parameters b and c, and it is expected to be a bit more difficult to do than the standard linear fits that we had done before. So let's give it a try. I'm saying fit r of x res.dat, and here the parameters are a, b and c. By the way, after I do this, I cannot go back to my original function f of x, because in this whole process the parameters a and b are going to change. Now I am getting a big problem. It simply says singular matrix in givens, which means it simply cannot handle a, b and c properly. Let's print a, b and c, see what happened. There is a value. Okay, b has come out to be negative, which perhaps means that the square root will end up with a negative value. So let's do one thing. I had actually started with a b value of minus 0.19. That was where the problem really came about. Remember, this b was already there from a previous fit. As you can see, b was minus 0.19 from the previous attempt to fit the straight line to the parabolic data. Let's start with the default values which gnuplot would usually have given a, b and c if I had not used a and b for another purpose before. Let's try doing this fit. Now it does do a fit, but if we look at the errors here, they're huge. 60% error, 40% error, 25% error and so on. Doesn't look very promising to me. And if I tried fitting this or plotting this, the function r of x along with res.dat, I should not be very hopeful that it is going to look nice. Let's see what it looks like. And definitely does not look nice. Okay. It didn't really understand the W well. I should have written W space L, but what I wanted to do was line width, LW. But you notice, this is apparently the curve of the function that I tried to fit to this data, which is pathetically bad. Now the reason why this is so bad is not very difficult to understand. If you think back about the function that I was trying to fit, the maximum value of this function occurs when f is equal to f0. And that maximum value, of course, when f is equal to f0, this denominator becomes just 1, the maximum value is v0. So the reason why this is coming out to be so bad actually is that the initial values gnuplot started out with were very, very far away from the actual values of the parameters. In this case, f0, which in our function is just c, is the value at which the data peaks, which is somewhere around 800 or so. And the value of the peak, which is the parameter a in our function, is around 25. So this is the reason why this is coming out to be so bad. Our starting values were way too far off, and gnuplot tries its best to start from those values, change the parameters in small amounts and get to as good a fit as possible and stop there. Now this is where you have to be a bit careful. If you're doing a nonlinear fit, you would have to give some kind of help to gnuplot. By help, I do not mean that you have to tell gnuplot what the value is, but you have to give it an estimate. So, at least you have to start close enough. Say, in this case, A would be around 20. I don't know exactly how much it is, I don't care. Around 20 is good enough. C, the value of x at which this peaks, should be around 800. Once again, I am not being very careful about where exactly the peak is. It is, as you can see, a bit beyond 800, but that will be taken care of by the fit function anyway. I could estimate the value of b, essentially the width of this, or really the quality factor for this resonance curve, but I don't really need to do all that. If I start with a and c, and a b value which is back to, let's say, 1, it should not turn out to be too bad. Let's try fitting now and see what happens. Now I am getting some errors, around 10% for this, 2% for this, quite a lot less for C. I should be reasonably confident that this graph should not look too bad. And although 10% error in B may look big, but you should realize the data file has rather wild fluctuations. So while this is a resonance curve, there are a lot of errors here, and the 10% error is not that bad. To see whether this is any good, let's try plotting the res.dat function with the new value, or with the old function r of x, with the new values of the fitted parameters a, b and c. Remember, gnuplot has already changed the parameters A, B and C in this process, so I do not have to go and tell gnuplot that A is this, B is this, C is this. It's already inbuilt. And let's see what the graph looks like. While you may not think that this is an exact fit, and of course it isn't, it is not too bad a fit either. Given the wide fluctuations which the data has, this is the best you could get. The lesson here is you can fit both linear and non-linear parametric dependencies, or rather could do both linear or non-linear least squares fit using gnuplot. The algorithm which gnuplot uses is one of the best algorithms in the business for this. You don't have to write any code for that, you just have to use the fit command. The important thing is you have to tell gnuplot which function to fit, what data file to fit, maybe which columns to use, even take some mathematical combinations of the columns by making use of the using command properly. And you could also fit for a range, and you could of course tell gnuplot which parameters will vary. Just to sort of illustrate that, let's say I want the graph to go really through this peak value, which is around 24.25. So let's say I will put A to be 24.25, which is the peak value in the graph. And let's say I don't really care to get the best possible fit, but I want the best possible fit where A is fixed at 24.25. And now I will fit the data again, but this time I will fit it via B and C. So what I am telling gnuplot is change B and C as much as you want, but do not touch the value of A, because that's not in the list of parameters via which you are doing the fitting. So I've got a fit now, and let's see how good this is going to be. This of course is not going to be as good as the previous fit. I don't expect it to be, but it will actually keep the peak value sort of intact. And if for some reason you are more confident of the peak value than the other values, this might very well be a good thing to do. Now there are many more complicated fits you could do. For example, you might have one more column of data here which in your data file which tells you how big the errors or estimated errors in each data point is, and then you could actually weight contribution of each data point to the final error which you are trying to minimize with the inverse of the error. So the points which have less error are given more weightage, the points which have more error are given less weightage, and so on. You can actually do all of that, but that is going to be a bit more complicated. You can of course refer to gnuplot's own help or the web to see how that's done. For the time being, let me wind up this particular video here. Bye bye and happy gnuplotting.